This is section 4.4, and in this section we are going to talk about properties of definite integrals. In the previous section we learned about the definite integrals. In this section we are going to talk about the properties, and we address the following objectives. Use the properties of definite integrals to find the area between curves. Solve applied problems involving definite integrals. And determine the average value of a function. And so let's start with the theorem number 5. So please take a look at this graph here. We have the pink one is the line that represents the graph of the function f. And by a previous section we learned that the definite integrals represent the area between the curve below the curve and the x-axis. So in this case the yellow area here represents the integral from a to c, so that's the definite integral from a to c of f of x dx. Now please notice that we can divide this interval AC into two sub-intervals, interval AB and interval BC, and create appropriate representation of definite integrals. So the first area here would be represented by the integral from a to b of f of x dx. The second area here is represented by the integral from b to c f of x dx. In other words, what it says here, this theorem, is that we can divide the interval of integration as we please, and then we can find the sum of two definite integrals in order to figure out the total integral. And why do we do this? Why would we like to do this? Well, because we know that nothing is perfect, and sometimes in the calculus we have the function defined as piecewise function. So let's take a look at the following example. We need to find the area under the graph of y equals f of x from -4 to 5, where the function is defined as piecewise defined function, which means that we have, well, two pieces. We have the line, horizontal line at y equals 9 for all x's less than 3, and we have part of a parabola for all x's greater or equal than 3. So if you take a look at the graph here, we are looking for the area below the the line and below the part of the parabola here. So basically, in order to find this, we need to figure out how to represent it, how to figure out the how to set up the integral, I would say. So in order to do so, we can split, as you see, from this one here, we can split the interval of integration. The entire interval is from -4 up to 5. We can split it by taking the sub-interval from -4 up to 3, and then from 3 up to 5. And this way, our integral from -4 up to 5 can be calculated, because again, if you get back, we have two different formulas for this function. We have one is y equals 9, the other is y equals x squared. So to make this integration possible, we split the interval of integration into -4, 3, and then 3, 5. And this way, of course, we need to figure out the corresponding function. So we know that for negative 4, 3, the function would be 9, because you know, the piece defined for numbers less than 3 was 9, and this is the piece that was for greater than 3. So we splitted the integral into two sub-integrals, and this way we can easily calculate this by, you know, taking the antiderivative and evaluate those. So the antiderivative of 9 is at 9x, and we evaluate it at negative, at the limits of integration, negative 4, 3. Antiderivative of x squared is x cubed over 3, and then again evaluated at 3, 5. Well, the simple calculation leaves you with 95 2/3. So this is the good example that shows you the reason and meaning behind the theorem 5 we just saw at the beginning. Now this is a quick check for you. Make sure that you pause the presentation right now and try to figure out this by yourself. So you need to find the area under the graph of y equals g of x from negative 3 to 6, where g of x is a piecewise defined function. Again, for x less or equal than 2, it's x squared. For x greater than 2, it is 8 minus x. So the 2 belongs to this interval negative 3 and 6, so probably it will be a good idea to split this integration over two intervals, from negative 3 up to 2, and then from 2 to 6. And this way we need to choose now the right formula for g of x here, and the right formula here will be, well, the interval negative 3, 2 is for x is less than or equal than 2, so that's the x squared, and then from 2 to 6 will be 8 minus x, sorry. So basically here we see you know what happens. We found this, and then we look for the antiderivative. Antiderivative of x squared is x cubed over 3, or 1/3 x cubed, and we evaluate it at negative 3 and 2. And then we evaluate 8x minus 1/2 x squared at 2, 6. Well, again, the simple calculations yield the final result, which is 27 2/3. Again, if you have questions, just put a question mark and I'll address all your concerns during the class meeting. Okay, and then this is a quick check too. Well, this one is I wouldn't say more complicated, but it requires more steps to solve. So for this example here, you need to evaluate an integral from 0 to 7 of an absolute value function. And we know that the graph of the absolute value function is always above the x-axis. Now it can take different shapes. So we need to be very cautious here, you know, how to proceed with a function like this. So let's start with definition of the piecewise of the absolute value function, which is the piecewise defined function. We know that the f of x is greater if 2x minus 1 is greater than 0, which yields, you know, the maybe I should write it down here explicitly. So we know that, okay, if 2x plus 1, oh, minus 1, sorry, minus 1 is greater or equal than 0, then we have exact value, you know, 2x minus 1. If 2x minus 1 is less than 0, then we have this value with minus, which will be minus 2x plus 1, or 1 minus 2x. So basically, if you solve this inequality for x, you will have, okay, 2x is greater than or equal than 1, or x is greater or equal than 1/2. That's why, you know, you got this x greater or equal than 1/2. And here we have, for, again, we solve this, so it will be x is less than 1/2, and that's the part. So we know that if the value under the absolute value is a positive or 0, then the absolute value function is exactly the same. If it's negative, then the absolute value is negative in front. We put minus in front of it, which yield 1 minus 2x. Okay, so here we have the piecewise defined function, and again the piece that divides the interval 0, 7 is equal, is just 1/2, right? So if we continue, we split the integration from 0 to 1/2, and then we take the function with minus, which is 1 minus 2x, and then from 1/2 to 7, and we take 2x minus 1, and then we find the antiderivative of 1 is x, antiderivative of 2x is x squared. We evaluate at 0 and 1/2, and here we have antiderivative of 2x is x squared, antiderivative of 1 is x, and this is at 1/2 and 7. Then we do the quick evaluation, and this yields 42 and 1/2. Okay, another property of definite integral, and this is under theorem 6. What if we would like to find not the area below some function, like below f of x, but we would like to find the area between two functions? And the assumption is that one function needs to be greater or equal than the other. And in this case, you see that the blue graph of f of x is above the red graph of g of x, which means that f of x is greater or equal than g of x over this interval, because we don't know what happens at the left part or the right part. We just know that, you know, within this interval AB, well, f of x is greater or equal than g of x, because the graph of f of x is above the graph of g of x. And that's actually the quickest way to verify which function is greater and where. Just graph them. And then the area between the region from A to B is given by a definite integral f of x minus g of x. And see, guys, when you look at this, it does make sense, because, you know, okay, if we mark the area below f of x, so that's the area, right? But we are not interested in finding this area. So what, from this area marked, we just subtract the area below g of x. Okay, we subtract this one here, and this way we are left with only yellow dashed area here. So this is very useful theorem. Again, if we are looking for the area between the graph of two functions, then that's how we need to proceed. We need to verify which function is above which, so which function is greater than the other, and then proceed with the formula. Okay, so now let's take a look at the example. We need to find the area of the region that is bounded by graphs of two functions. First one is a linear function, f of x equals 2x plus 1, and the other is quadratic function, g of x equals x squared plus 1. So we need to first look at the graph. In order to find, you know, this area, we need to verify which graph is above which, and then find the area bounded by the graphs. They didn't give us an interval, so probably when we graph those two functions, we will see the area that, you know, is between them. Well, in order to solve this and find out, you know, precise a point of intersection, then what we do, we set up the both function equal to each other, so we set up 2x plus 1 equals 2x squared plus 1. This way we will know the points x at which those two intersect. So when we solve this, we put everything on one side, so it's x squared minus 2x, and it's equal 0, right? So then we are looking for points of intersection. So in order to solve quadratic equation, we factor. So we have x minus 2 equals 0. So we know that the points of intersection are at x equals 0 and at x equals 2. The only one thing is to find out y. So y corresponding to x equals 0 is 1. And then y corresponding to x equals 2 is 5. And we can figure out this taking, substituting 0 to any of the function, to the first or the second, and because that's the points of intersection. Having those, we can make precise graph and see how the area between the graph look like, and we see it here. So now we know that f of x is greater than g of x over interval. So here we have that f of x is greater or equal than g of x over interval, and the interval is given here from 0 to 2. Having those, we just follow the formula. We follow the formula from the previous slide, and we can calculate, we did this, okay, and we calculate the integral. So it's gonna be an integral, and then from the upper function we subtract the lower function, or from the greater function we subtract the smaller function, and we simplify it, and then just find antiderivative, which is here, and do the simple calculation to get 4/3. So 4/3 square unit is included between the graphs of two functions. Again, I go through this quickly because I assume that you cover this, you know this material from Calculus 1 class. It is just the revision. So let's take a look at another example. A clever college student develops an engine that is believed to meet all state standards for emission control. The new engine's rate of emission is given by E of t equals 2t squared, where E of t is the emission in billions of pollution particulates per year, and t is the time in years. The emission rate of a conventional engine is given by C of t 9 plus t squared, and the t is the same times in year. So we have new engine and we have conventional engine, and well, what is the question now? So oops, right. We can start with the graph. They didn't give us a question yet, but okay, if we look at the graph, well, we see that the graphs intersect at some point. It looks like 3, but we need to verify this algebraically. We cannot just get it from the graph. Oh, here is the question. At what point in time will the emission rates be the same? And what is the reduction in emission resulting from using the student's engine? Okay, so for this one here, well, the emission rate will be the same when E of t is equal C of t, and apparently from this graph here it looks like 3, but even if you can figure out something from the graph, please make sure that you include algebraic calculations for it. So in order to find the emission rates at the same level, we just set up E of t and c of t equal to each other. So e of t was 2t squared, and it's equal to 9 plus t squared. And we solve the quadratic equation by factoring, simplifying and factoring. So t is equal 3 or t is equal -3. Now the negative sign doesn't mean anything because t is a time in years, so we just reject this solution. So that's not the solution here. We only consider t equals 3. So we can conclude that the emission rates will be the same when time is 3 years, and it agree with previously shown graph. Okay, and then for B, the reduction in emission is represented by area between the graphs, E of t and C of t, and we remember that C of t was above E of t, and the interval was from 0 to 3, so we just set up the integral from 0 to 3, and we subtract from 9 plus t squared, we subtract 2t squared, we simplify it, and then we do the simple calculation to get the answer 18, and 18 represents billion pollution particulates per year. Okay, so now we are gonna talk about the average value of a function, and we start with the definition. So if the function is continuous over a closed interval AB, then its average value is given by the following formula. So y average is given by 1 over b minus a. b minus a, as you remember, this is the length of this interval, and then an integral from a to b f of x dx. Okay, the formula looks mysterious. You are not required to know how this formula was derived, but you are required to get some understanding of this formula, what it means. So let's take a look at the example here. We need to find the average value of a function x squared over an interval 0 and 2. So basically when we follow the formula, we go 1 over b minus a, which is 2 minus 0, and then the integral from 0 to 2, and we have the function x squared dx. Well, this is no problem to calculate the value, right? We take 1/2 and then we find antiderivative of x squared, which is x cubed over 3 within 0 and 2. And then we just substitute value 2 and 0, and we get that the answer is 4/3 or 1 1/3. If you take a look at the graph, well, the graph will give you a meaning to this to the theorem and to this example. So what is the average value? Y average is 1 1/3, which is located in here. And when you see the graph here, you see that, okay, the area, the value, the average value for the function is the value of the function that divides the graph in such a way that actually this purple and this brown value, actually no, the purple and the yellow value are the same. So that's the average value of the function. Now for let's take a look at another example. Rico's speed in miles per hour t minutes after entering the freeway is given by the velocity function here, and from 5 minutes after entering the freeway to 25th minute actually I should say, what was Rico's average speed? How far did he travel over that time interval? Okay, so what do we have to figure out here? What is they ask us to do here? Well, if if you see the average speed, and the speed is given here, that's the velocity function or speed, then it means that we need to apply the average value formula for this average speed. So go ahead and let's do it. So let's follow the formula. We have the interval was from 5 to 25, so we have 1 over b minus a, which is 25 minus 5, and then the integral from 5 to 25 of the speed function or velocity function. And I hope you can use it as an exercise, but it's fairly easy to calculate those, and the result yields 68 and 3/4 miles per hour. And then this is the average speed. And then we need to find how far Rico traveled over the time interval 5 and 25. So basically, we note that time is given in minutes, not in hours. So since 25 minutes minus 5 is 20 minutes, this is 1/3 of the hour. So the distance traveled is 1/3 times the average speed, which was 68 and 3/4, and this is 22 and 11 over 22 miles. So basically that concludes the previous example, and go ahead and follow this example, the previous example, and try to do this by yourself. This is a quick check, so it's designed for you to check your skills, to check your understanding. And in this problem we have the temperature in degrees Fahrenheit in Minneapolis on a winter's day is modeled by the function. And that's the function, where x is a number of hours from midnight, and we need to find the average temperature in Minneapolis during this 24 hours period. So basically what you have to do, you need to set up the right integral, just follow the formula for the average value of the function. So please pause. And the average temperature is, well, the 1 over 24 minus 0, and then the integral is from 0 to 24 of the function that models the temperature in Fahrenheit. And then you need to do the simple calculations to get the final answer. So this example concludes section 4.4. I went quickly through it. If you need more time, just please pause, write down the questions. I'll be more than happy to answer them. But the chapter you should cover. You should be familiar with the section 4.1 up to 4.5. So that's why I went through it quickly. In the summary of this section, we learned that we can, split the interval of integration into 2 sub-intervals and calculate the integral over each sub-interval. Also, we learned that the area bounded by the graphs of 2 functions, f of x and g of x, where f of x is greater or equal than g of x over this interval, is given by the following formula. This is very useful formula. And the third thing we learned the average value of a continuous function over the interval AB is given by 1 minus b minus a over 1 over b minus a, and then an integral from a to b f of x dx.